All right, so this is our second half of the lecture. If you were not here yesterday, we had introduced this concept called the mean value theorem, and what we had talked about was the idea that there exists some sort of theorem here that says that if I have a function that is continuous and differentiable, and continuous because we're dealing with a value theorem, and differentiable because this particular value theorem deals with slopes, then there is a spot such that if I have a closed interval between A and B, that if I drew a secant line between those 2 points, essentially what it says is that there's a tangent line whose slope is also going to be the same as that secant line, that the secant and the tangent will be parallel to one another. And we find the slope of the secant line by using the average rate of change, or the slope formula, and we find the slope of the tangent line by using the derivative at that point C. From that, we've discussed how what exactly graphically we're looking for a parallel tangent. We've discussed how to use the mean value theorem, and that it's a unique theorem when it comes to value theorems, in that we are looking for we can use it to find specific values because there's a formula attached to the mean value theorem. We've done a few examples, and we've got one more that we're going to look at, and you should have started this one already. But it was this idea of f of x is equal to x to the 2/3. So like all problems, we want to consider whether or not f is continuous on the interval, so in this case -1 to 2. And we also want to know if f is differentiable on the interval, and this is the open interval -1 to 2. Now for continuity, we're dealing with x to the 2/3. This has no situation where I have to worry about the square root of negative numbers. There are no holes, there's no asymptotes, there's nothing like that. So I know this is continuous, so I don't have to worry about u. But I do want to deal with differentiability. For those of you who don't know what this particular graph looks like, give me one moment, I will bring up this graph. But if you're not 100% sure on what this graph looks like, this is kind of a family of functions that you want to get to know. But when I bring up this particular function, yep, decimals, good stuff. If I look at the function f of x, and we set that equal to x to the 1/3, and I know that was 2/3, but you'll see right here that x to the 1/3 has a vertical tangent line at x equals 0. So we're already seeing that there's a spot where there's non-differentiability. If I change this from x to the 1/3 to x to the 2/3, we can see that this function comes down to a point and then bounces up, which means that x equals 0 is a point of non-differentiability. If I go back to my function now, if I look at the interval includes 0, which means we have a point of non-differentiability. In fact, I would make my statement that f of x, oops, come on board, that f of x is not differentiable at x equals 0. Include that it's a cusp. Therefore, MVT cannot hold. And I'll use cannot hold. You can use, we can't use MVT. You can do a lot of different words there. But the idea is that you cannot utilize MVT because it's non-differentiable. We like those, so we don't have to do very much work. You will notice I specifically identified the point, and I wanted them to know what I was looking at, so I wanted to include that cusp or sharp turn to verify that, hey, I do know what this function looks like. Again, I could try to go through and prove this, but this becomes really hard. This is where knowing your families of functions is almost a requirement in this class. So now let's take a look at some AP exam questions. We get all sorts. For instance, number 1 here, the function f is defined by f of x equals x cubed minus 2x squared plus 4. The mean value theorem of f on the interval 2 to 4 guarantees the existence of the value c. So we're already saying that MVT guarantees something, so that means that we're good on the continuous and differentiable. We could still state that. We can say f is continuous on 2 to 4. We can say f is differentiable. Always a good thing to be practice on that. 2 to 4. So the question just asks, where is that f? We guarantee that some c exists where 2 is less than c is less than 4. I'm going to give you a second to answer the question such that f prime of c equals. I'm going to give you a second to try that out if you'd like. Just make sure to pause the video here so that you have some time to think before I put up the answer. All right, if you haven't paused the video there, I'm going to go ahead and I'm going to solve this out. First off, it says such that f prime of c is equal to something. So I know that I need to find f of 4, and I want to find f of 2. So let's do those. F of 4 is going to be 4 cubed minus 2 times 4 squared plus 4. Oh my goodness, this is crazy. So what is 4 cubed? 2, 4, 8, 16, 32, 64. That should be 64 minus 32. That's 16 times 2. Plus 4, so that's 32 plus 4 is 36. And here I want 2 cubed minus 2 times 2 squared, swoop, plus 4. That should equal 4. So I know, and this is where things get fun, be very careful that you're answering the question, because this would be f of 4 minus the f of 2 over 4 minus 2 is equal to the f prime of c. Now there will be some people who will take a derivative of f of x and they'll plug into c and they'll find a c and they're going to get an answer. In fact, I believe the answer turns out to be 4 if you do it incorrect. But look at what it's asking for. The question just says, what is f prime of c? So that's 32 divided by 2 is 16. And if you write out the statement, you can see f prime of c is 16. So be careful to read the questions. It's very easy to overread these, overanalyze these, and make some strange mistakes. The next one is a free response from 2011. We have a continuous function f defined on the interval from -4 to 3. Find the average rate of change of f on the interval from -4 to 3. There is no point c from -4 to 3 for which f prime of c is equal to that average rate of change. Explain why the statement does not contradict the mean value theorem. So basically what it says is there is no c that makes mean value theorem work. So why is it that mean value theorem is not contradicted? I'll give you, go ahead and pause the video. Give yourself a second to think about that question. And then go ahead and hit play when you're ready. So what you should have looked at is that from -4 to 3, we have a function that is continuous, but we can see that f is not differentiable, once again, at x equals 0. By the way, at x equals 0 is not always the case. At x equals 0 or at x is equal to -3. And what I would do is I would make sure to include that this is a sharp turn and that this is a vertical tan line. By the way, just as an aside, this particular question, if you would have only stated 1 point, this is directly from the AP test. As long as you included 1 point that's correct, you would actually get all of the credit. You would not need to note both, although don't be surprised if they give some sort of partial credit for identifying both of those pieces. On to number 3. If f of x is equal to the sine of x over 2, then there exists a value c on pi over 2 to 3 pi over 2 that satisfies the conclusion of MVT. Which of the following could be c? So now you'll notice the difference between 3 and 1. I've got which of the following could be c as opposed to f prime of c. So now I've got to find that value. Again, I will give you a moment if you'd like to pause the video before hitting play again to decide, see if you can do this. All right, so They've already told me that I can use MVT, but again, I take a look at this. There's no divide by zero. It's signed, so I know this is a smooth curve. So I am cool with this being continuous and differentiable. So I need to evaluate the f of 3 pi over 2, which will be the sine of 3 pi over 2 over 2, or the sine of 3 pi over 4, which is the positive square root of 2 over 2. And then I want to also find the f of pi over 2, which is the sine of pi. If I do pi over 2 over 2, that becomes pi over 4, which is also the root 2 over 2. I also want to find the f prime of x, which is a chain rule, sine of x over 2. So make sure we're taking care of that. The derivative of sine is the cosine of x over 2 times 1/2. So now what I need to do is I can take the f of 3 pi fourths minus the f of pi fourths over 3 pi fourths minus pi fourths. And I know that this seems dumb because I know that you all can recognize that this is going to equal 0. But you actually want to write that out to prove that you understand that the average rate of change, this phrase here is connecting the concept of an average rate of change to an instant rate of change. So I'm making sure that the person who's grading me understands that I have a solid background in the mathematics of what mean value theorem is actually telling me, that it connects average rate of change to instant rate of change. This turns out to be 0. Root 2 over 2 minus root 2 over 2 is 0. So that equals 1/2 the cosine of c over 2. Remember, I changed the x to a c because I'm looking at a specific value. I multiply the 2 over, and I want to know when the cosine of c over 2 is 0. Now this is maybe a little more complicated than what we're used to, so here's what I do. I don't think of cosine of c over 2. What I do is I think, when is cosine 0? So the first thing I do is I get rid of the cosine. So c over 2 is going to be, cosine is pi over 2, 3 pi over 2, 5 pi over 2, and it's all of the odd pi's over 2. Then what I do is I realize to get to my answer is I need to not be c over 2, I just need to be c. So I'm going to multiply each one of these by 2. So pi over 2 times 2 is pi. 3 pi over 2 times 2 is 3 pi. 5 pi over 2 times 2 is 5 pi. And technically there's an infinite number of solutions here. But you can see the only one that's between pi over 2 and 3 pi over 2 is pi. I know the trig gets scary, so if you have questions on that one, feel free to ask. All right, I think we might have one more set of questions. Again, I will give you a moment. In fact, why don't you try out both 4 and 5, pause the video, and what I will do is I will go straight through 4 and 5 here as soon as you hit play. All right. So we're taking a look at 4. And our first one, 4, we want to know which of the following could be false. There's only one that could be false. The other ones actually have to be true. You'll notice we make a statement about continuous. We make a statement about differentiable. So because of continuity, we know IVT and EVT hold. And we know by differentiable that MVT has to hold. So when I look through this, I'm looking for statements. A and B both look like MVT statements. And then these two look like EVT statements. So I want to look at the EVT situations first. F has a minimum value from A to B. If it's a closed interval that's continuous, EVT has to be true. So that and this both have to be true statements. So we're stuck between our MVT A and our MVT B. The best way to deal with this is which one is more specific. If you look, A says that the derivative is just equal to some slope between A and B. B says the derivative has to equal 0. you'll notice that B is really specific. So what we realize is that the more specific one is always going to be the wrong answer. It's kind of this concept that as I put rules onto something, we become more stringent. This is Rolle's theorem, which only works if f of A equals f of B. You'll notice that if f of A and f of B are equal to each other, this will still equal 0, which means A is not only includes B, but any other possible number that exists here. So the one that is not true is B. So lastly, we've got the table below gives the value of functions f, its first derivative f prime, its second derivative f double prime for the selected values of x. The function f double prime is continuous for all real numbers. Is there a value of c from 2 to 3 such that f double prime of c equals 6? So these are the tough ones. This is the monster. These are the things that'll eat your lunch. And the reason is it's really tempting to pick the wrong value theorem. So now that you have mean value and intermediate value theorem, you're going to have to make a decision on which one we want. So between 2 and 3, does f double prime equal 6? So if I look between 2 and 3 and I look at f double prime, you'll notice that the smallest value is -3 and the greatest value is -1. So what that means is that if I wanted to use IVT, since the function since f double prime is continuous, all right, f double prime is continuous, that means f prime was differentiable. And since f prime was differentiable, f was also differentiable, so we can kind of backtrack all those. But if I look, if f double prime is continuous, and my value is from -3 to -1, but 6 is outside, IVT will fail. So this is where students go, oh, nope, doesn't work, IVT failed. But if I look at f prime of x, f prime is continuous on 2 to 3. Let's take a look at that. Let's think about that. From 2 to 3, if f double prime is continuous, then that means that f prime has to be differentiable. And if f prime is differentiable, then we can say that f prime is continuous. I'm going to put since f double prime is, or since f prime is differentiable. And it's kind of like reading this backwards. F prime is differentiable on 2 to 3 since f double prime is continuous. And we wind up getting this cool relationship that if something is continuous, then the derivative of the function that made that, so if f double prime is continuous, if I go backwards a step to f prime, then that becomes differentiable. So I can actually do this backwards compatibility concept. All right. So why is that useful? Well, because now I can answer this question for f double prime. If I think of f prime of 3 minus f prime of 2 over 3 minus 2, that should equal the second derivative at some c value. So you'll notice now we've got a connection of the rate of change, average rate of change of the f primes is equal to the derivative of f prime at c. We changed our scope a little bit here. Well, what is this going to equal? Well, f prime of 3 is 5 minus the f prime of 2, which is -1 over 1. There it is, folks. F double prime of c has to be 6. So somewhere between 2 and 3, f double prime has to equal 6. This gets even cooler now, because if I were to ask you a question like, since f double prime has to equal 6, could f double prime equal 4? I can actually now use the intermediate value theorem and the mean value theorem all at the same time and say, well, yes, it definitely does. And in fact, I could ask, how many times does f double prime equal 4 on 2 to 3? And you could actually say twice. Because I could reach 4 by going from -3 up to 6. So once from 2 to the 6, and then another time from the 6 down to the -1. And you can see that EVT and IVT and MVT interact with one another to make this really cool mix of things that once I've proven with MVT another number, which usually gives me a max of a higher or a lower value, that I can use IVT to prove that it happens more than once. Now that's a little bit more than the basic stuff on there, but I hope that that was at least a little bit helpful. You've got a couple of questions that are inside your calculus tracker that deals with the mean value theorem. Give them a shot, and I look forward to your questions when I get back tomorrow. Hope you have a wonderful day.